All right, I know you are unable to see your own tests and the work you did, but I'd like to review the exam 2 solution. The first two problems on the test, we use the derivative formula to calculate the derivative. All right, so here we have a quadratic function. All right, here's our point, our x value and y value, which we'll need for the equation, the tangent line. All right, so here's our derivative formula, right? F of x plus h minus f of x, where we see x and f of x, we need to substitute x plus h. As you see here, there's f of x, and notice again I use the brackets as grouping symbols just to make sure we're careful with the algebra. All right, so if you go through this correctly, all right, ultimately you should get down to this point here. Now again, at this point we cannot, we have h in the denominator, we cannot substitute h is 0 here, but once we factor out the h, we get this expression, and now this is our derivative function, 2x plus 2. All right, and then for the equation, the tangent line, all right, we need to substitute the x value into the derivative function to get our slope of the tangent line, which is minus 4. Then here's our y value and x value. All right, just be careful with the negative signs there. And then eventually we will get to our slope-intercept form, y equals minus 4x minus 14. All right, in problem 2, all right, now we have a rational expression. All right, and here's your x and y values here. Again, I'm going to use our limit formula for the derivative function. All right, this is f of x plus h minus f of x divided by h. Here's our LCD. So remember, we need to multiply numerator and denominator of each of these expressions by the missing factors in the denominator. So for this first term, I'm going to do x plus 1. For this term, x plus h plus 1. And again, the subtraction, you have to be careful. So I'm going to add the parentheses here and then distribute that negative, as you see with the terms over here. Now, we should get some cancellation. We're left with a minus h. That will cancel with the h here when we turn the division of h here into multiplication of the reciprocal of the second term. All right. Now we can do direct substitution, let h go to 0, and this is our derivative function, minus 1 over x plus 1 squared. Again, we'll substitute the x value given into this expression. We'll get minus 1/4 for the slope of the tangent line. Here's our y value. Here's our x value. We get it into slope-intercept form. All right, so now we're done with the derivative formula. From this point forward, we don't want to use that formula to find derivatives. All right, but before we get to that, all right, we'll look at a couple derivative concepts. All right, the graph of a function is given. Sketch the graph of its derivative. Now, one of the hints I gave in class was that look for the points where there would be 0 values for the derivative or slope of the tangent line. So this point here at minus 3 and 3, if you look carefully, here we will get horizontal tangent lines. So I can fill in those 0 points. And then if we think about it going from left to right, here we have a generic positive slope that goes to 0. That's this segment you see here. And then here, this whole segment is really a generic negative slope at a particular value, which you would draw in this fashion between the 0 points. It has to be negative here. And then as we approach this 0 point, that negative becomes smaller, closer to 0, and then it becomes positive again. Okay, and so that's the segment that we see here. All right, this is multiple choice, so the figure shows the graph of a function. All right, and at the given value of x, does the function appear to be differentiable, continuous but not differentiable, or neither continuous nor differentiable? All right, so notice we do have a continuous function here, all right, but it is continuous but not differentiable because this is what we would call the corner point. Remember, we saw this with some of those graphs with our derivative. All right, when the slope of the tangent line changes abruptly around a point, all right, the two-sided limit does not exist for the derivative. All right, so there it is not differentiable at this point. All right, now find the equation of the tangent line. From this point forward, we want to find our derivative function quickly and easily using our rules. So, all right, here they give us the x value of 2. All right, we will need the y value, so I'm going to plug in 2 into this equation, get minus 1. We'll need the x and y values for the equation of the tangent line. So find f prime of x, plug in the x value, which we get is 8. That's our slope of the tangent line. And again, there's our y value, there's our x value, here's our slope of the tangent line, slope-intercept form of the equation, y equals 8x minus 17. All right, next derivative, e to the x times secant of x. Now, this is a product rule problem. So, derivative e to the x is e to the x, then times the second function secant of x. Then, now we take our first function f of x, multiply it by the derivative of g of x, which is secant x of tangent of x, and always pull out that common factor, simplify. In this case, you should have e to the x secant of x times 1 plus tangent of x. Okay. Now, problem 7, we want you to find the second derivative. Now, one thing I've said is a lot of times there's sort of a pre-manipulation of a function that we can do to make the problem simpler. So what I want to do here is take this x, 1 over x to the fourth, and rewrite it with a negative exponent. So a little adjustment there. And now we'll just use our derivative rules, right? Or power rule, really. Here's 14x minus 4 times minus 1 is plus. And then we subtract 1, x to the minus 5. Now, I've added a sticky note here. I did make one little mistake here in the derivative. And oh, by the way, e to the minus 1 is a constant, so that goes away. But this second part, all right, y prime here should be 14x plus 4, x to the minus fifth, right? The minus 4 times the minus should be plus 4, x to the minus fifth. And then when we take the second derivative, all right, that minus 5, all right, 14x will become 14. And then minus 5 times plus 4 is minus 20, and then it's x to the minus 6. So just notice that final answer, a little bit of a typo there. 14 minus 20x to the minus 6 is the correct answer. Remember, the idea here is to write 1 over x to the fourth as x to the minus fourth. That pre-manipulation allows you to avoid the quotient rule entirely. Makes the problem much simpler. All right, now in problem 8, we do have to use the quotient rule to find the derivative. All right, so our f of x is 4, g of x, x squared minus 3. So again, notice I'll use the parentheses for each part of the quotient rule here. All right, derivative of 4 is 0 times g of x, then minus 4, and the derivative of g of x is 2x, all divided by g of x squared. And the only thing we'll be left with in the numerator is minus 8x divided by g of x. All right, so there's our x and y values, 2 and 4. Plug in the x value to get the slope of the tangent line. So we'll plug in 2 here. You should get a slope of minus 16. And again, same thing we've seen in a bunch of other problems, right? There's our y value, our slope of the tangent line, and our x value. Go to slope-intercept form, minus 16x plus 36. All right, number 9, find the derivative. Again, we can rewrite this problem a little bit just to make it a little easier to avoid the quotient rule. First, x tangent of x, that is really a product rule problem. But 1 over sine of x, I can write as cosecant of x with that reciprocal relationship. All right, so you'll see in brackets here, this is the product rule. All right, so derivative of x is 1 times tangent of x, and then we have x times the derivative of tangent of x, which is secant squared x. And then derivative of cosecant is minus cosecant cotangent. All right. And this is really just your final expression. No common factors to be pulled out. All right. Number 10. All right. Again, with this first term, we will have a little product rule problem. These other terms you can really handle individually. So product rule, right? Derivative of t to the 8th is 8t to the 7th times cosine of t plus t to the 8th derivative of cosine of t minus sine of t. Again, I'll put the brackets around that part just to not make a mistake. Then derivative minus sine of t minus cosine of t, and then square root of t. Remember, I could write that as t to the 1/2 and then apply the power rule. All right, so then this is our final answer here. Technically, you could pull out a factor of t to the 7th here. I didn't do that. But you could if you wanted to. And then we can go back to radical form here. T to the minus 1/2 I could write as 1 over the square root of t. Okay, number 11. Now, here we want to find the equation of the tangent line with the trig function. We had done a practice problem like similar to this in class. All right, so a couple things. One, they give you an x value of pi over 2. We're going to need the y value. So plug in the x value. Cosine of pi over 2 is one of our special values, which is 0. So 3 plus 0 is 3. So this is our x and y value, the point we're going to get the slope of the tangent line at. Now, derivative of 3 plus cosine of x, 3 will go away. Derivative of cosine is minus sine of x. We substitute that x value of pi over 2, and so now we have minus sine of pi over 2, which will end up being minus 1. So now we have our three pieces. Here's our y value. Here's the slope of the tangent line. Here's the x value. This will be it in slope-intercept form. And with your special value of pi, don't feel that you have to combine these numerical terms. All right, these are really the exact values. We can leave it like that. All right, last problem on the no calculator part. All right, this is a graph of a position function. So moving south would be going down, moving north going up. And so we really just want the time intervals, really, all right, our sort of x values or horizontal variable values. All right, when's the object moving north? So it would be moving north from time 1 to 3, all right, from time 5 to 7, and time 12 to 14. Some of you put these in parentheses, like an interval notation. That's fine. When is the object moving south? All right, well, we have three intervals there. 0 to 1 on this segment, 3 to 5 on this segment, and 9 to 12 on this segment. Okay, so there's those values there. And then when is the object stationary? All right, we can see between time 7 and 9, that's when the object is stationary.